All right. We're going to start with probably what most people consider the most difficult chapter, chapter 4, chemicals and calculations in the chemical equations. The mole concept in atoms. So atoms, if you hadn't realized it, are really small. Okay? So the unit of measurement for the mass of an atom is the atomic mass unit. So they randomly assign carbon-12, the isotope carbon-12, a mass of exactly 12 AMU. 1 AMU is 1.66 times 10 to the minus 24th grams. So the periodic table gives all your weights in AMU. So atomic weight of one fluorine atom is 19.00 AMU, according to your periodic table. What would be the mass of this one atom in grams? So 19 AMU, fluorine, times 1.661 times 10 to the minus 24th grams is 3.156 times 10 to the minus 23rd grams of fluorine. Now, normally, we can't, well, actually not normally, we can't weigh out that much. It's too small. So we're going to go with finding a collection of atoms as a mole. 1 mole of atoms is 6.022 times 10 to the 23rd. Now, the mole is just a counting device. If I told you, give me a dozen eggs, you would give me 12. So when I say dozen, you say 12. When I say mole, you're going to tell me 6.022 times 10 to the 23rd. That's called Avogadro's number. It's one you have to memorize. So a mole of anything is 6.022 times 10 to the 23rd of whatever that is. So if I had a mole of oranges, how many oranges would I have? 6.022 times 10 to the 23rd. If I had a mole, or if I had 6.022 times 10 to the 23rd avocados, how many avocados would I have? 1 mole. But since they're avocados, it's probably a guacamole. No? Okay. All right. I know, but so the mole is a counting unit, and we abbreviated MOL. I don't know how much saving we're getting by dropping that last E, but we abbreviated MOL. So it's a unit that defines an amount of something. Like I said, a dozen defines 12. I usually go with a gross, but most people don't know a gross means 144. So we can go back to our fluorine atom. 1 atom of fluorine is 19.00 AMU. And since AMU is 1.66 times 10 to the minus 24th grams, times 6.022 times 10 to the 23rd atoms per mole of fluorine, I could say a mole of fluorine weighs 19.00 grams. So notice if we look at the periodic table, it tells us fluorine is 19.00 AMU. If we go through this calculation, 1 mole of fluorine atoms weighs 19.00 grams. It's the same number. Okay? This is called the molar mass. How many grams per mole? So if you look at carbon on your periodic table, it's 12.01 AMU. If I say go weigh out a mole of carbon, you weigh out 12.01 grams. The same number. The molar mass is the macro scale that we deal with, weighing out. The atomic scale is in AMU. So we can use the following conversion factors. Density converts between grams and milliliters because density is equal to mass over volume. Atomic mass units convert between AMU and grams. Avogadro's number converts between moles and numbers of atoms. And molar mass converts between grams and moles. So you have a whole bunch of conversions we can do depending on what we need to find out. Calculate the number of moles of sulfur represented by 1.81 times 10 to the 24th atoms of sulfur. We know 1 mole of sulfur is 6.022 times 10 to the 23rd atoms. So we can write, from any inequality, you can write 2 conversion factors. 1 mole of sulfur for 6.022 times 10 to the 23rd atoms. 6.022 times 10 to the 23rd atoms of sulfur for 1 mole. So we want to know how many moles is in 1.81 times 10 to the 24th. So if we look at this, and let me, before I mess it up, I can go 1.81 times 10 to the 24th atoms of sulfur. I want to know how many moles. So I have to choose one of these conversion factors to get rid of the atoms. So if the atoms are on top here, they have to be on the bottom in the next one, which means I'm going to choose this conversion factor. 1 mole sulfur, 6.022 times 10 to the 23rd. It's really difficult to write with this pen. So now it's, and the answer is going to be around 3. .01. No, actually, I didn't memorize it, so it's not like I had it memorized. All I did was, oh, bless you, convert this to 23rd, which makes this 18. 18 divided by 6 is roughly 3. I convert, this is times 10 to the 23rd. I made this times 10 to the 23rd. So if I make this smaller, I have to make this bigger. So I move the decimal point over 1, which makes it 18. 18 divided by 6 is 3. So I knew it was 3 and some change. Old people math without the calculator. Questions? Oh my God, what is that? This should be in Blackboard under Chapter 4, kind of written out. This is I call it the stoichiometry roadmap. Okay? And we'll come back to that a little bit. But this, if you have this written down, you can do all the problems really easily. And I believe that's in Chapter 4. It's posted. It's called Stoichiometry Roadmap. It's a Word document. Print it out. Yeah, funny. Because we go, as you're going to see, grams of A to moles of A, moles of A to particles of A, moles of A to moles of B, moles of B to grams of B, moles of B to particles of B. And like a map, we have streets and stops. So if we figure out where we start and where we end, we can do just about any stoichiometry problem. That's similar. The book has something similar. I like this one. I like this version. It's a different version. Now I'm watching to see what we were doing on the phones there. Really? I really wouldn't check them, but you're not supposed to have your phones out in class anyways. Thank you. Because if you check your percentages, it's a little deceiving because you have all 250 points for lab or somewhere around there. That's going to go down during the semester. I can guarantee you that. So what is the mass in grams of 3.01 moles of sulfur? So 1 mole of sulfur is 32.06 grams. How do I know that? I go to the periodic table. Sulfur is 32.06 AMU, and I said the molar mass is the same number in grams. So again, we can have two conversions, 1 mole per 32.06 grams, 32.06 grams per 1 mole. So 3.01 moles times 32.06 grams per mole. 3 moles weighs 96.4 grams, 96.5 grams. So we've just went from moles of A to grams of A. And over here on the board, I'm going to reconstruct. So we went from moles of A to grams of A. And how did we do that? We multiplied it by the molar mass. So to go in that direction, we multiply by the molar mass. If I want to go of grams to A to moles of A, guess what I do? If I want to go backwards. Divide by the molar mass. Just the opposite. So now we just constructed one of the roads in the map. Calculate the number of atoms of sulfur in 1 gram of sulfur. Well, I know what's the relationship between particles or atoms and moles. 1 mole of anything contains 6.022 times 10 to the 23rd. So if I'm going from moles of A, and I'm going to call particles of A, so that could be atoms, or if we talk about molecules, I'm going to multiply it by Avogadro's number, 6.022 times 10 to the 23rd. Am I confusing you? Or why? No, go ahead, tell. This? We did the first conversion, right? We went from moles to grams, moles of sulfur to grams of sulfur. And we did that. Let's go back. I don't want to lose anybody here. Let's go back here. So we went from moles to grams. We multiplied it by the molar mass, right? So moles of A, we're going to, A just stands for sulfur in this case. To grams of A, we go and see the arrows going down. If we're going to go in this, we're going to multiply it by the molar mass. If we want to go the reverse direction. If we're multiplying going down, we're going to divide going up. Okay? So that takes care of that part. Yes. And I know that 1 mole of anything is 6.022 times 10 to the 23rd. So to go from moles to particles, and I'm going to multiply it by Avogadro's number. 6.022 times 10 to the 23rd. All right? All right, so if I go back the other way, I'm going to divide by Avogadro's number. Okay? It's slightly different than the way the book does it. It's the same formula.
What I'm confused on is moles of A and particles of A. How do I know?
1 mole of anything is how many particles? 6.022 times 10 to the 23rd. So if I have 2 moles, how do I figure out how many particles? By 2, right? So to go from moles to particles, however many moles, I'm going to multiply by Avogadro's number, right?
I don't know which one which. I don't know which particles of which. Where do I start?
Okay, let's look at this problem. No, not this problem. Calculate the number of atoms in 1 gram of sulfur. Okay? So here's where the problem is. I can go, if I look on the road map, I can go from moles of A to particles of A, right? But I wasn't given moles. I was given grams. I got to go from here.
I got you. I thought you had to start on one side to go off.
Nope. I'm going to start here and end up over here. So that is my route. So I have how many streets? 2. I'm going to have 2 steps. No? Okay? Oh, I'm talking to her. I'm sorry. So, step 1, I'm going to go from, what was it, 1 gram? I'm starting with 1 gram of sulfur. I know from the map I got to go, what's my next stop? Moles of sulfur, right? I'm going from here, I got to go to here. Exactly. So I'm going to go to moles of sulfur. This is on the top. This has got to come here to the bottom, so it cancels out. 1 mole of sulfur, I know, weighs 32.06 from the periodic table. So this is 32.06. This is essentially dividing because this is in the bottom. So now I'm here. The next step is I want to get to atoms. So I got to go over here, multiply by Avogadro's number. So I'm going to go 6.022 times 10 to the 23rd atoms of sulfur per 1 mole. You see the moles cancel, the grams cancel, I'm left with atoms. So it's 1 times 6.022 times 10 to the 23rd divided by 32. 1.8 times 10 to the 22nd. So that's what I just wrote. Oop. 1.88 times 10 to the 22nd. Can I what? Can you type it into the calculator? Are you asking me, can you? Yeah. Why wouldn't it be? You got to remember when you do this, well, this part isn't so bad, but if that was in the denominator, you have to put it in parentheses. Unless you have a cheap calculator that I have that has a button that takes care of it for you. So now we have half the map. Okay? I'm just going to come over here and tell you that moles of B is the same as the other side. Okay? So it's symmetrical. Yes. Yeah, you have to start with something. The key is figuring out where you're starting and where you're ending. Follow the map. Right, it may not. Yes, we could start out anywhere on the map. Where did I get this? Sulfur is 32.06. That's the molar mass. To go from moles of A to moles of B, we use coefficients, and we'll talk about that later. But once you get the hang of this, it's pretty simple. When I worked as an organic chemist, we'd spend a week figuring out a series of reactions to make a compound. This part was the last 5 minutes. But you'll see. Calculate the number of atoms in 1.7 moles of boron. So here's a problem for you. What are we starting with? Moles. So we're going to start here, moles of A. So I'm going to start here. And I want to know the number of atoms, so I'm going to end here. One street. So it'll be 1.7 times Avogadro's number. 6.022 times 10 to the 23rd. (1.1 times 10 to the 24th). Yeah. See if I'm right.
What was the mental math you just
I don't have a faintest idea. See if I'm right first. 1.7 times 6.022 times 10 to the 23rd.
We can't do the 10 to the 23rd.
Yeah, you can. If you got the right calculator, you can. This is a good time to check to see if you got to know how to do exponents on your calculator. 1.024 times 10 to the 24th. Okay, so I said 1.1. That was close.
How did you do it? Did you do it on your phone or on a different thing?
I told you get those scientific calculators, those dollar calculators at the dollar store. Nope, that's the case. That's it. Make sure it's a scientific calculator. 6.022. Hit the little EXP button. 23rd. There you go. times 1.7, 1.02374 times 10 to the 24th. Yeah. Yeah. Dollar Tree. And I usually buy like 4 of them at a time. Because if the batteries go, I don't change the battery, throw it out. Or sometimes the button will get stuck. But, you know, Casio sells them for about 10 bucks, and you don't need to get an expensive one. Just make sure it can do logs and scientific notation. Steal the kids. Problem 2, find the mass in grams of 2.5 moles of sodium. Where's my green pen? There it is. So for problem 2, where are we starting? Moles. Where are we ending? Grams. Multiplied by the molar mass. Molar mass of sodium is 22.9, or essentially 23. So it'd be 2.5 times 23, 46, 46, and 16 is 62 and a half. Did I come close? No? Oh, wait, 46, I'm sorry, 46 and 11 should be 48, 40, 58 and a half. 57 and a half. Okay. 2 times 23 is 46. Half of 23 is 11. Yes, 47 and a half, yes. Grams to moles? Which one are you talking about? We're starting with moles and we're going to atoms. So we're starting here for number 1, and we're going to here. So all you can do is multiply by Avogadro's number. We didn't have to go through grams. Okay. In number 2, we're again starting at moles, but we're going to grams, so we're only going down this street. So we're going to multiply by the molar mass. I haven't gotten it. Okay. Calculate the number of atoms in 5 grams of aluminum. So there we're going to start at grams, and we're going to end here. That's going to be 2 steps. We can't go from here to here. There's no street. We have to go from here to here, grams to moles, then moles to atoms. So if we start with number 3, we have 5.0 grams of aluminum to moles per gram. 1 mole of aluminum is, I'm going to say roughly 27. It's actually 26. And when you do this, use the numbers in your periodic table. Don't use approximations, and don't use the ones up here, because these go out a little bit further. So now we're at moles. 6.022 times 10 to the 23rd atoms per mole. So it's 5 times 6.022 times 10 to the 23rd divided by 27. I'm guessing 5 goes into 16. 12 times, so that's a little bit more than 5. 1.1 times 10 to the 23rd. 1.115. Okay. Not bad for an old guy. You afraid of leaving fingerprints? Oh, okay. So everybody see what we did on number 3? Everybody okay with that? Because later on we get the chemical equations, it's going to come into being. Number 4, calculate the mass of 5 million atoms of gold. So there we're starting at particles of A, and we're ending at grams of A. What does what? A is whatever the first element we're choosing, or the first compound we're choosing. So A is a variable. In this case, it's gold, and the last problem was aluminum. A or B? Doesn't matter. It's symmetrical. If it's B, you would go this way. You still get the same answer. Okay? I just choose A because alphabetically, as far as I know, A becomes before B. So the first one I start with, I call A. And right now, we're just using single compounds. We haven't gotten to equations yet. So here we would go, here would we go in a mess. 5 times 10 to the 6th atoms times 1 mole, 6.022 times 10 to the 23rd atoms times, gold is roughly 197 grams per 1 mole. I don't think I can do that in my head. Let's see, that's 14 minus, wait a minute, 7 minus 17, 6, 36. I'm guessing, again, 36 times 10 to the minus 17. 3.6 times 10 to the minus 16th? No? Not even close? What? I think you're wrong. All right. 5 times 10 to the 6th divided by 6.022, 23rd, minus 18. Yeah. 197 divided by 2.37 times 10 to the minus 19th. Okay. Let's do it across the top first, okay? 5 million yeah, times 197 is equal to 9.85 times 10 to the 8th. Divide that by 6.022 times 10 to the 23rd. (1.6 times 10 to the minus 15th). You forgot to put it in parentheses, didn't you? When you did division here. Oh, what did I say? I said 3 something, didn't I? Okay. Where's the 18? Oh, I did it a different way before. If we do 5 million divided by 6.022 exponent 23rd, then you get 8.3 times 10 to the minus 18th. What we said was 1.5 times 10 to the minus 16th? Or 1.6. Whoops. Wrong one. Uh-oh. Very small amount of grams. So that's how the book does it. It's kind of grams to moles, you divide by the molar mass. Moles to grams, you multiply by the molar mass. Moles to particles, you multiply by Avogadro's number. Particles to moles, you divide by Avogadro's number. Same thing I got up there. It's just written a little differently. Either way works, whatever floats your boat. So, chemical formula. It's a combination of symbols of various elements that make up the compound. We have the formula unit, the smallest collection of atoms that provide two important pieces of information: the identity of the atoms or ions, and the relative number of each type of atom or ion. So water, H2O, tells us we got hydrogen, oxygen. It also tells us how much. 2 hydrogen for each oxygen. It's not H4O2, it's H2O. It's got to be the simplest number. Hydrogen is H2. Hydrogen exists in nature as H2. It doesn't exist as H. There are 7 diatomic molecules you have to know. Hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. They all exist in nature as diatomic molecules. Later on, you have to remember that because when we do chemical equations, and I say hydrogen plus nitrogen gives you ammonia, you have to know hydrogen's H2, not H. And nitrogen's N2, not N. Otherwise, you can get the wrong equation, and everything gets screwed up from there. Sodium chloride, NaCl, tells you have 1 ion each of sodium and chlorine. Calcium hydroxide, you have 1 ion of calcium and 2 ions of the OH, polyatomic ion. So if we look at the elements, if we want to calculate the molar mass for calcium hydroxide, it would be 1 calcium, 2 oxygen, 2 hydrogen. The 2 outside the parenthesis multiplies everything on the inside. So, ammonium sulfate, NH43SO4. The ammonium ion is 1 nitrogen and 4 hydrogen. Sulfate is 1 sulfur and 4 oxygen. So if we look at the compound, and they did it wrong, that's why I got it saved there, has 3 nitrogens in it, 12 hydrogens, the 3 times 4, 1 sulfur, and 4 oxygens. So if you want to figure out the molar mass of that, you have to add all of those up. Copper sulfate pentahydrate, so it's a hydrate. It contains water molecules as part of their structure. That's why they're written separately. So if you want to figure out the molar mass of this, it'd be 1 copper, 1 sulfur, 4 oxygen here, 5 oxygen here, 9 oxygen, and 10 hydrogen. 5 times 2. 5 times 1 is 5, plus the 4 here is 9. So you'd add all that up to figure out what the molar mass of copper sulfate pentahydrate is.
So when it's written like that, you have to multiply by number in front of the element.
Yeah, this multiplies everything. And you'll actually do an experiment working with copper sulfate pentahydrate. And there it is. It's blue. You buy it at Home Depot. It's used called root killer. If you have roots growing in your sewer, you dump that in there. If you heat it, you drive off the water, it turns white. And if you let it sit there, it'll reabsorb water from the atmosphere and go back to blue. So that water goes in and out. So the formula weight is the sum of the atomic weights of all atoms in the compound, represented by its correct formula, expressed in AMU. So the formula weight of H2O is 16 plus 2 times 1.008, 18.02 AMU. That's the formula weight. The molar mass is the same number, but grams per mole, 18.02 grams per mole. So again, on the microscopic level, AMU. On the macroscopic level, grams per mole. So the formula unit is the smallest collection of atoms from which the formula of a compound can be established. So what's the molar mass of NH4 ammonium phosphate, NH4,3PO4? Hopefully they do it. We have 3 nitrogens, 12 hydrogens, phosphorus, and 4 oxygens. So you add them all up, comes out to be 149.1 grams per mole. So if I ask you to weigh out 1 mole ammonium phosphate, you'd weigh out 149.1 grams. Okay? 14.01, and that one you have 14.007. Well, yeah, like that one has 14.007. Oh, we don't have the other. One of the periodic tables we had here that was even more expensive went 14.007046. That's why I told you use the one in your book, because all the connect problems use the ones in your book. So if you use this, you might come up a little bit off because of rounding. Molar mass is the mass in grams of 1 mole. So the molar mass of carbon is 12.01. And you can see the one on the wall is 12.011. The molar mass is 12.01 grams. And we know 1 mole of any element contains the same number of atoms, 6.022 times 10 to the 23rd. Okay. Let's take a break.